second lecture for this sustainable infrastructure monitoring with AI-inspired machine learning. As you have seen on the lecture 1, we have talked a little bit about the infrastructure. We have talked about a little bit of the monitoring, that how different types of monitoring are important and what could be the benefits of those. And for this one, we will mainly talk about AI and its application, more into the talking about the different kind of sensor integration. Then we will also see different kind of anomaly detection and what are the main difference of those kind of anomaly detection. Some little bit of examples definitely with it. And we were mainly interested in the case of or applications of structural health monitoring. So we will mainly seeing the anomaly or the cases which is mainly applicable for structural health monitoring. And definitely please remember that we are most of the cases which we are considering, they are mainly applicable to infrastructure monitoring. And then we will also see a little bit of energy efficiency optimization and challenges and future direction as per the lectures goes on. So as we have seen that this is the lecture 2 where we have said these are the main 4 aspects of the AI and applications which we will be looking into. And among those, the first one always comes around the data collection techniques. So we will try to understand the data collection techniques which will form the foundation of the health monitoring. As we said that when we start the monitoring, the first thing which is very, very important for us, that what to monitor. And when we say what to monitor, then definitely data is something which we need to monitor, and then definitely with the process we will see how to monitor and what will be the further process to monitor those data, right? So the first thing, as I said, that when we talk about the infrastructure monitoring, the data is a very, very important factor, and collecting those techniques or data collecting techniques are one of the important foundation for the structural health monitoring or the SHM techniques. And depending on the applications generally, we need to collect and we need to analyze very different types of data. For example, if you think about the vibration for high-rise buildings, or if you can think about the long span bridges, or sometimes the radioactive or X-ray of any nuclear facilities, collecting this data is always help us or kind of taking you as a path to build a detailed picture of the defects, right, or their sources, and even predict the life expectancy or for structure or the component which you are kind of monitoring, right? So one of the main categories of the data collection is, there are different ways to do that. The first one, so I have tried to identify the main important ways that how could we collect the data. First one is definitely the manual data collection. So this is a very old or we are doing it for several years, and this is a very established way of doing this. So the first one is, as I said, the manual data collection, and this involves human observation. Definitely, it's very, very important. Human inspection and measurement using the handheld or remotely installed instruments like we say X-ray machines or sensors. So data is the first captured locally for this kind of cases, and then it has been transferred to a central repository for analysis. That's the very basic or old way of collecting the data, and we call it as a manual data collection. However, manual data collection also has a lot of limitations definitely, and that's the reason we kind of have different other ways of collecting the data. So it can be very labor intensive. Definitely you can understand that it's always going to be human observation. So definitely you will need to put a lot of labor, and then prone to human error. Basically there could be a lot of uncertainties, there could be a lot of error due to the human measurement. And then definitely difficulty in hand to reach locations. So there are definitely certain locations of some breaches or some kind of structures where you cannot reach. So those kind of places are always difficult to collect the data manually, and then may cause a delays in fraud detection definitely, and or make it hard to track the defect of the growth, right? And this is the reason that is the many industries are now moving towards more into collecting the data automatically or remote data collections methods, which we will now talk about in the next one. So this is the very beginning of the way that we have started collecting the data manually. And then now we move from more manual data collection to the automated data collection techniques. And automated data collection techniques, they are, as we saw in the previous lecture, so we are using generally sensors like IoT, we are using and then remote monitoring system to collect those data, continuous process and accurately, definitely. And in that case, we may not need human invention, especially during collecting the data. Definitely for analysis, we do need that, but during that process you can actually do that without human intervention, right? So this allow us to obtain a real-time data. This also help us reliable information on the structural health or the environmental condition and even construction progress. So which in turn actually improves the safety, the efficiency, and some way proactive project management. So basically these are the main advantages you can see when we move from the manual data collection to automated data collection, right? And then there are, when we do that, then there are definitely certain tools, certain techniques that how we kind of do this one. So one of the very important and user friendly and mainly used one, I think we all know, is the sensor and instrumentation. And among those, definitely strain gauges, they help us to understand the deformation or strain in structure. That some way we are kind of use it to assess the structural integrity, right? And another kind of sensors which we use a lot for the structural health monitoring is the inclinometer or the tilt meters, and they kind of help us to understand the track of the slope or the tilt of the slope, and that help us when we talk about the landslide, when we talk about the structural movement, those things. And then another important one is the load cell. The load cell, they also help us to detect the force or the loads on the structure to monitor the stress and the potential overloading condition for when we talk about the food or the some buildings as well. And then another kind of second type of tools which we need to kind of do the automated data collection rather than the manual data collection is the data logger, right? Data logger and the communication system. So these are the basically they kind of store it and they kind of transmit the collected data from the sensor. So the sensor which we have first of all used it to collect the data, and then we are using the data logger or the communicated sensor, and they will be helping you to enable the real-time data transition. So you real-time you collect the data, and immediately with this instrumentation by real-time you can transmit the data and allow a continuous monitoring system and immediate responses to the anomalies, right? So this integration is vital when we think about proactive management, as we are talking about, and ensures a very high reliability during the process of the data collection. So that's one of the tools which we use when we move from the manual data collection to the automated data collection, right? And then in essence, when we think about this automated data collection, not only it overcomes the limitations of manual methods, but it also helps us to enable the smarter decision making with accurate and real-time data, right? And then again, another important tool which we use except the sensor and the instrumentation is the surveying technology, right? That's also important, that how or what is the process of you are actually monitoring the data through the sensor, right? There are several ways we do that in modern infrastructure projects where we cannot reach using the manual method. But there are lot of advanced tools we do use a lot, and among those the main important ones or widely used ones are UAVs. We do quite use UAVs, the small aeroplanes, we have seen those, or the drones, or LIDAs, or the GNS, those are the satellites. They have become very, very essential when we talk about infrastructure monitoring. And this actually technologies help us to also 3D model and laser scanning, right? So they are also very much advanced when we talk about modeling those data in 3D or scanning the laser. And they are very crucial for accurate mapping and progress tracking over the large or difficult to reach areas. So drones, they are equipped with videos, they are also equipped with thermal sensors, they can collect highly comprehensive and real-time data which actually help us or offer us the insights of the structural integrity. They also kind of help us to understand the environmental conditions or construction progress, and this capability actually greatly enhanced when we are taking some kind of decision making, or they also help us the project safety, it will help us on the efficiency. And again, as it's a real-time monitoring, so it will also help you to kind of reduce the time. It is also, and you can see that in the beginning we have talked, during the process we may not need a lot of labor, so it's also some way help you to cost effectiveness, right? The traditional manual surveying method. So in essence, you can see that the surveying technologies, they represent a big step change how we monitor and how we manage the large scale projects. And please remember, here we are talking about not the small scale infrastructure monitoring, but we are talking about mainly the large scale projects where you are kind of building a big bridge or are building a lot of buildings together, or we are talking about a big project together. So that is the very easiest way or convenient way that we can actually monitor the progress throughout this sensor, collect the data, and process it further. And now if you will try to kind of talk about the third category of data collection. So first we talk about the manual, right? Second we have talked about the automated one. Third is the remote sensing technique. That's also been quite a use when we talked about the SHM technique especially. And where do we generally use it? So remote sensing is actually help us to collect the data from geographically isolated. So that's where it kind of comes into the picture, where we kind of have to monitor some infrastructure which is geographically isolated, or some kind of hazardous location where human or any kind of other perspective cannot reach without needing of physical access. This will also provide you a real-time overview of the infrastructure health, which is crucial for improving the safety, extending the lifespan of the civil structures, and they also reduce the maintenance cost, as I said, and they will help you to prevent the catastrophic failure. That is quite obvious because you are monitoring the data, so you will definitely kind of help, or it will kind of help you to prevent the catastrophic failure, right? And there are several key technologies which we generally use. The main or the important one you can see is the sensor-based monitoring, which we use quite a lot when we talk about remote sensing technique. For example, you can think about vibration-based techniques. So vibration sensors, they always help us how our structure is dynamically respond to certain kind of loads. They also help us to understand some kind of environmental factors. So by observing the deviation in natural frequency, I mean, those are the main factors we look into, right, when we talk about what exactly we are looking into the vibration sensor. So we kind of try to look into the natural frequency, if there is any changes in natural frequency. We also look into the stiffness, we also look into the damping ratio, right? And from those we can actually identify the early signs of structural issues. So this approach is especially suitable for long span structures, as I say. For the big structures, long span structures, something like breaches, where traditional inspection method or manual technique does not work, and they can be challenging, they can be risky. So as you can see in this particular figure here, the diagram shows us how the sensors, such as those displacement, tilt, strain and vibration sensors, how they kind of transmit the data, right? Wirelessly. And please remember that here we are talking about they are transmitting data wirelessly to a central gateway, and that's a cloud or the server storage, right? And from those storage, this will actually help the engineer to monitor the structural health monitoring in real lifetime or real time and immediately act proactively, right? That means before any catastrophic failure happens, before any damage happens, engineers will be able to tackle if there is any kind of crack or any kind of initiation of damage could possibly be there. So again, as I was saying, if we will go back to the previous one, when we talk about the remote sensing technique, there is a several keys and technologies which we do use. Vibration-based monitoring is definitely one of those very, very important ones which we use a lot. But then there are also other ones. I think all of you, if you are kind of working on structural health monitoring, you must be aware of all this. Then the second one is the fiber optic sensor. It's quite important, it's quite obvious because of the fact that they can monitor multiple parameters simultaneously, and that's where the fiber optic sensors are quite different compared to the piezo sensors, compared to the vibration one, right? So that's the special ability of the fiber optic sensors they do have, that they kind of gain the wide application because they can monitor the multiple parameters simultaneously, right? Such as strain, temperature, even acoustic emission. So in acoustic cases, they have been used quite a lot. And they are very highly resistant to electromagnetic interface, and they can also function into the harsh environments. When there is a lot of temperature changes, you can see some where the PJT is little brittle in that case, but in those particular cases, we kind of use fiber optic sensors quite a lot. And then, as I said, the electromagnetic interference, and they can also function in, for the large scale, they can also function in the complex structures like tunnels. So please remember that we are very much concerned about the large projects or large infrastructure, because that's the place where the manual monitoring or the simplest way how we monitor does not work, because we need a lot of costing, we need a lot of other complexity. So main of the cases we are interested to understand how things when become complex, how we kind of take care of it, right? So as I said, yeah, fiber optic sensors are quite good when we talk about the large structure, when we talk about the complex structures. And here you can see this particular images here, and this illustrates how longitudinal and transverse sensing cables they can be embedded to provide comprehensive coverage across the whole structure. So especially for the case of tunnels, we do use fiber optic sensor quite a lot, right? And then I think the another important one, which is the piezoelectric sensor. I think if we work with SHM, if we work with energy harvesting, I think all of us must have used at some point of our life piezoelectric sensor. It's definitely cheap. It's kind of quite user friendly, and these sensors work on principle that if certain materials generate an electric output, right? When you subject it to some mechanical stress, that means you give some mechanical stress, you get some sudden electrical output. And they are often used to understand the localized damage detection, and they are very small in size, right? And they are very highly sensitive. They have a lot of versatility, and piezoelectric sensors can be embedded, they can be surface mounted. That's the way generally we kind of use this to monitor the stress waves and to identify the damage early on. But then definitely there are a lot of disadvantages of piezoelectric sensors as well, right? We cannot use it for a long period. We cannot use when the temperature is another concern, because they are very brittle, right? So that's where kind of fiber optic sensors play around. That's where the other sensors play around. But when we think about quick monitoring, when we think about local damage, especially when we are talking about, then PCT actually works really good, and it's very easily available. That's also and easily managed as well. So that's where some way it's kind of becoming one of the famous ones compared to the other two. So if you will see all of these technologies here, you can see that together this technology, they always help us to obtain a high resolution. They kind of help us to understand the real-time data about the structural health, and even in challenging or large-scale environment, where there could be a harsh environment, there could be a large-scale structure. So these sensors some way kind of work according to that line. Okay, and this is I think one of the PZT sensors I have shown that basically how does it work. This is the main PZT things, how it works. It's generally been embedded into the structure. Sometimes it's inside into the concrete beam, and some way it looks like that. And then you kind of introduce some kind of mechanical stress, and you get electrical outputs. That's how generally PZT sensors work. So now I think this is quite easy for you to kind of give an answer, because just now we talked about it. So when we talk about the PZT sensors, which one do you think is the best one to kind of talk about, or best kind of to use it? C? Are you sure B? Yeah, B is the one, because we are very much interested about the local damage detection under certain kind of stress. We are talking about mechanical stress here. That's the best space when we talk about it. When we talk about temperature change and a huge range, they talk about humidity. Definitely we cannot do that. When we talk about capturing the video, that means you are getting through the laser using this drone. We cannot do that using PZT, right? So B is the correct answer. So now comes one of the very important part of this is that anomaly detection. That how do we actually kind of understand that your data or the data you are getting, that some way is different than the idealized data, or some way you feel that okay, this range is kind of giving us a non-damaged section, and how we are differentiating. And through this particular part, you will understand that it does not always depend on the data. It also depends at what situation you are getting the data, and what is exactly the other circumstances which come around collecting the data. It's always not about okay, fine, this one is very different to the this date N1 range. It's not always like that. So that's what we kind of will see, that how there are different ways to understand that there are some kind of anomaly in your data, right? So an anomaly is very much essential in a data point or in a pattern that does not follow the ordinary or expected behavior, as I was saying. Detecting the anomalies is very critical in many of the fields, such as if you think about fault detection or fraud. When we use some kind of credit card, that's a fraud prevention, and this absolutely structural health monitoring, because it helps us to identify the usual behavior before it becomes a major issue, right? So here we will try to look into the different kind of anomaly detection, and we will try to see that what are important, what circumstances are important. So the first one is, if you can look into that, is the point anomalies. If you will, so let's try to see the example first here. So there are different types of anomaly detection. We are firstly focusing on the point anomalies, right, which is the very simplest one. A point anomaly generally occurs in a single data set here, right? So now if you will look into the point sigma 1, sigma 2 and sigma 3 here, it is outside the normal region of N1 and N2, right? And they are considered as the point anomalies because they deviate from the normal cluster data point, which is N1 and N2. So as a real life example, think about like credit card. This is a very simplest example about credit card fraud detection, right? If you are kind of tracking the amount spent, maybe you have some kind of amount, you always use it. So when the transaction with an usual high amount compared to the normal sending, goes up, you always get a call from the bank, right? Because that's the reason when they understand, okay, fine, there is some kind of fraud detection. So this is something a very simplest way that the points does not kind of fit into the sets of data. It goes outside of data. We do not see about any other circumstances. We are only interested about this is the point that does not fit into the normal area. That means there is some kind of detection, and that's the reason we kind of raise the concern, right? So that's the very simplest one. So the point anomalies are very essential outliers, and they the single unusual data points that can identify or that can indicate the error. They can unusual events or fraudulent activities. So this is the very simplest way that we identify there is some kind of issue which we need to monitor. Okay. And then comes the different or the challenging perspectives of detecting the anomalies. So one of the important one is that the contextual anomalies, right? So when it happens, it generally happens when the data instance is anonymous in one context, right? But perfectly normal in another. So in one word, you can say that anomaly depends on its context. It also depends on its neighborhood, right? For example, if you think about a high temperature, that might be okay during the summer, right? But that's not anomalous when we think about the winter. That is like an issue, right? So it is the same value for the context, right? When the context changes or the interpretation will definitely change, right? So contextual attributes, they actually define the context or the environment of the data point. For instance, the spatial data set, if they are longitudinal, if they are latitudinal, they will provide the location context in that case. And then there is another types of one, which is the behavioral attributes, right? So this is all coming under contextual anomalies. So there are two types of one. One is the contextual attributes, another one is the behavioral attributes. Behavioral attributes is basically nothing but describes the non-contextual characteristics of the data point. That means you can using some same spatial example like average rainfall at a location. That is a behavioral attribute, but it's what you are actually measuring, right? When detecting the contextual anomalies, we focus on whether our data is behaved usually in its given context. That means when we are talking about the rainfall of a certain place, so what is the situation of the particular city, country we are talking about? So the choice to use the contextual anomaly detection, that depends on how significant the contextual factors are, how important those are in the target area, right? And how usually the context can be established. In some cases, you will see it is very, very straightforward. You don't need to use too much of brain. But in some cases, where context is not there's not clearly defined. Those are the times that can be difficult to measure. So let's see one or two examples of how possibly it could look like. Some visual example of this. So this is the graph, right? It shows the monthly temperature data over the several years. So now if you notice this point T1 here, right? And if you notice this point T2. So you can see that the point T1 and point T2 value is almost same, isn't it? So what is different here? The time, right? The month is different. So that means this illustrates that the anomalies are not just about the value itself, but also about the context in which the value occurs, right? In other words, you can say that during the December, getting a low temperature is always like, it's very normal, right? But when you get it somewhere like March or June, that's not normal. That's the kind of examples when we talk about the contextual anomalies. This is exactly why contextual anomaly detection is important. It helps us to identify the anomalies that standard points anomaly detection would miss, right? Especially when you time series or spatial data. So those are the important ones. And then there is another one, except the contextual one, except the point-wise one, which is the collective anomalies. And you will see that they are very, very important when we talk about the structural health monitoring. So they are basically occurs when a group of related data points is anomalous as a whole. So you will see that maybe 1 or 2 points are okay. But when you think about as a sets of data, then you will be finding out that the groups of those related data points is anomalous because of the fact that even the individual points, if you will some way look into that, may not appear to one individual, right? And that's the time, or in other words, is the pattern of the data which instances together that signals something is not normal. And that's the thing we call as a collective anomalies, right? So if you will look into this figure here, you can see that the example, this is basically a example of ECG output, and actual premature contraction actually happened there. So it's basically how the heart rhythm is actually behaving. So collective anomalies are especially common in, as I said, in time series data, network activity logs, sensor outputs. That is very, very important. When patterns matter very importantly, more than a single reading. So you will see the single reading may be like not look unusual, but when you see the pattern in the time series, especially looking into the data in the time series, you will see that it can be critical in some areas, and healthcare is one of the very, very essential one when we talk about healthcare monitoring, cyber security, structural health monitoring, where we really need to kind of understand the sequentials of that rather than individual events, which is like signal potential problems, right? So these are the main three types of anomalies which could possibly happen. The first one is definitely the easiest one. The second one is the generally we always contextual one. We always kind of get into that. But it depends on what context you get it. If it's very straightforward, then definitely you can identify, which is this one. You can definitely identify, okay, fine, this actually is fine, or it has some problem. But if your context is not identified clearly, maybe you can think about a region where if you kind of look back into this one, maybe you can think about a region, like maybe I could talk about Southampton, because Southampton can be actually cold during the summer and even during the winter. So if you are looking into that place, then it can be a little bit confusing that, okay, fine, you are trying to understand the temperature depending on the month, but it's confusing because you do not know that how it could possibly be, right? But when you talk about some places like Shimla, Darjeeling, it's quite obvious to understand. Or you kind of talk about some, eastern part or southern part. So if your context is very clear, you know what factors are important, then you are good to go. But when it is not, then things become little difficult. And then, as I said, the collective anomalies, when you try to analyze the data in time series as a frequency domain, time domain, when you're trying to analyze it, trying to analyze the sensor data, spatial data, then it becomes very, very important as well that you're collectively trying to look into how your frequencies are looking at, how your data are looking into. So that's the place. But the good thing is that it does not depend about any context. You need to just get the data and understand whether there are some kind of abnormality in your data, right? And that's the main techniques of identifying the anomaly, main three types, okay? And then definitely there are some methods, right? The methods of anomaly detection. The previous one I said that the technique, that this is the way we do that. Then there are some way we do that. The first one is statistical anomaly detection technique. That's also one of the very oldest techniques. That's one of the very most traditional methods we have used quite a lot. And they work by building a statistical model of what normal data possibly could look like. And once the model is established, a statistical interference test is being done, and that's being applied to check whether there is a new data that belongs to the normal data, or they do not look like normal data. And that's how we generally kind of identify whether there is any kind of anomalies which is being there. So statistical anomaly detection is a very simplest, oldest, and most used methods from the past so many years. And this approach actually includes a varieties of methods, like there are proximity based methods, there are parametric based methods, there are non-parametric based methods, there are semi-parametric based methods, depending on what parameters you are having. For example, if you think about parametric based method, that that data follows a known distribution. So you may know that your distribution is going to follow the Gaussian one, especially when you have too many stochastic data. You are kind of doing a lot of random analysis. You know that your distribution will look like a Gaussian distribution or normal distribution, right? So that's the way when you know your parametric distribution. But the non-parametric distribution is that you do not know. So I think, I don't know if you've heard about the fuzzy logic. So those are the techniques we generally use when we do not know about our distribution. So that's the way that we kind of take a rectangle, we kind of take a square also, and then we try to kind of imagine how our distribution could look like, and some will be kind of try to come up with an assumption. That basically is your non-parametric. So there are several ways you can do that, and that's been quite been used quite a lot. And now one of the famous one which we are using from past 5-10 years compared to the statistical one. Especially we use it when you kind of have a non-parametric or semi-parametric method. So it's the machine learning anomaly detection techniques. We also use quite a lot because we are talking about the large scale here, we are talking about the complex structures here, we are talking about IoT sensor, beach monitoring. So definitely we need the machine learning anomaly detection technique. And this methods actually automate the process of learning from the data, and instead of relying purely on statistics, we train a model distinguish between the normal and abnormal behavior. So ML-based techniques can be split into several categories. So on how the data can be trained. So the main one is the supervised one, semi-supervised one, and unsupervised one. And this makes the ML especially powerful when dealing with the large and the complex data sets, where patterns are not easily captured by simply the statistical method, right? Together, statistical and machine learning techniques, they kind of backbone of the modern anomaly systems. And now we will quickly look into the three important parameters of the machine learning anomaly detection technique. The first one is the supervised one. So the supervised anomaly detection is nothing but both the normal and the anomalous training data sets are labeled, right? So you know the normal data set, you know the anomalous data set, right? And this means that every instant the data set is already marked as either normal. So basically you know that which comes under normal, which comes under not normal anomalous. So you just pick it up, okay fine, this doesn't come under normal, doesn't come under normal. That's where you kind of know that, right? That's we call as a supervised learning. So using this information you can actually make a predictive model to distinguish between the two classes, and then you apply the model to the new data, then detect the anomaly. Similarly, you know this is my perfect data, this has some anomaly, you get the data, you put your data as per it is coming in, and then you take it, and then you make a predictive model, right? Very simple way of doing that. But it does have a challenges as well, because when we know the method becomes easy, it does also come with limitations, right? So the first one is definitely too hard to obtain and precisely level for anomalies. So sometimes it's very, very different to say that this is black and this is white, right? There could be always a gray range between black and white, and that's where the place and that's where the challenges come around here. That is sometimes little difficult to actually identify that okay fine, this is not perfectly, and that's where the supervised learning does not work out, right? And that makes your training really difficult and lead to like bias model. Then what you do is that as an engineer or as a mathematician, you kind of use your prior knowledge and you can say that okay fine, from my prior knowledge I feel that this could be a anomalous, and that's where the bias comes as a human, right? So that's the problem with, or the disadvantages with this kind of model. And it is also like often hard to obtain precise and representative levels for anomalies since they are like rare. Sometimes it's very difficult to understand on what basis we are identifying that this is not correct. So that's the issue with this. So basically, supervised learning, they requires a level. We will look into that before we get into the other one. So this is a very nicer way to show that what exactly it talks about. So supervised learning is to require a level normal anomalous data. Where when we talk about the semi-supervised one, it trains only on normal data and detects deviations during the interface, right? And when we talk about the unsupervised learning here, they uses no levels at all basically. They assume the anomalies are very rare. They assume that they differ from the majority of the data. But basically when we talk about the supervised anomaly detection, they works well, then you have label data is available. So when you know that this is my black, this is my white, my life is sorted, I know how to label that and I know how to predict that, right? Because the moment the challenges come, then the semi-supervised or the unsupervised methods come into the picture. But if you look into the real life cases, it's never easy to kind of say this is black or this is white. So that's the reason supervised learning, we don't use it quite a lot when we talk about our real life cases. That's the place where we use semi-supervised learning or the unsupervised learning in the real life scenario. Because that's the time we always face the challenges to identify our not perfect data, or we always may not have our not perfect data. So that's the place we use quite this one a lot. So as we said about the supervised learning, there is a semi-supervised anomaly detection as well. So in this approach, what happens is that the model is trained only on the normal data, right? So there is no anomaly levels provided during the training. So when we train the data compared to the previous one, we do not say this is not our perfect data. So we only level the, we only train the normal data, right? So later what we do is that later when the model is applied to the new data, anything that cannot classify as a normal is flagged anomalous. That's what we do there. Basically in the supervised one, we clearly differentiate, this is our normal data, this is our anomalous data. But in semi-supervised videos, we just train according to the normal data, and then we kind of put it into our next data. Whatever does not fit into that, we say this is some issue, right? That's how the unsupervised work. So we do not label anything as a anomaly data or something like that. Since we do not need the label anomaly, this method is more common than supervised method, because we only saying, okay, fine, this is black. We are not interested to identify what is white, right? So whatever does not fit into black, automatically going into white. That's some way, our life becomes easy, because we are minusing one of the point, and that's where the semi-supervised anomaly comes. And this is the reason that in the real life, it's been used quite a lot compared to the supervised one, right? And then comes one of the challenging one, but the most used one in the real life structure, that is the unsupervised anomaly detection. And here no training data set is required. So the model looks at the entire data set without labels, right? Without any kind of labeling, and assuming that the normal instances are much more common than anomalies. That is the kind of assumption we do in the unsupervised learning. So it tries to group the data based on the similarity, and then identify the data points that does not fit as anomalies, right? That's where this actually being done. This approach is quite useful, right? Because you don't need to identify what is white, you don't need to identify what is black. What you simply do is that you identify the bunch of data there, and then you see what does not fit around on the data set, right? And if that assumption fails, right, whatever you have assumed, if that fails, that means anomalies are more frequent than expected. So it can lead to definitely high false alarm rate as one of the disadvantages for this. And as I said, that this diagram is quite a good one to kind of look into that. So now, I have just talked about 3, which is like a little less, but if you will try to look into the machine learning techniques, that has been applied a lot in the development of the models. You can see that, and especially for the anomaly detections, you can actually identify those into 28 different anomaly techniques. And there are several ways to do that. There's ways of classification, there's a way of clustering, regression, optimization. But the main ones, definitely now it has been changed, maybe every year, there's always been add-on. The main ones, which have been used quite a lot, detect the anomaly, are totally 28. To build the models which are capable of detecting the anomalies. These techniques can be, as I said, they can be grouped into several categories, and each are having their own strength. Some can be good for small data, some can be good for large data. So classification methods such as you can see that super vector machines, SVM is quite famous, decision tree, Bayesian network, various neural network like CNNs, RNNs, or self-organizing machines. They all come under classical methods, right? And this is especially powerful when you have labeled data. You want to classify instances as normal or anomalous. That means for the supervised case, when you know what is your data. So these are the best ones when you use that, right? And then another one is the clustering data, right? The clustering data is the one which is, I think you must have used the k-means or hierarchical clustering or the fuzzy clustering, which is being used quite a lot. And these are very, very useful when you do not know how your distribution is like. That means unsupervised or semi-supervised? Unsupervised, right? That means, yes, that means very, very useful for unsupervised anomaly detection, or grouping similar data points or identifying the outliers. So that's how generally the clustering works out. And then, as I said, that there's other ways to do that, which is optimization and rule-based method techniques like generic algorithm or also some system, help to optimize the data to find the pattern in the complex data. Another one is the assemble methods like AjaBoost, which combines multiple weak learners to improve the detection accuracy. And then one of the very famous one is the regression techniques such as logistic, linear regression. They are actually kind of models or relations between variables to stop the deviation, right? So this diagram, you can look into that how broad or versatile the machine learning approaches are tackling in anomaly detection. I'm very sure there are now a lot can be are always being added, but I've tried to identify the main ones, and then there are a lot of branches definitely alongside with that. And the right choice of techniques, as I always say when you use the machine learning model, the right choice of technique, the right data what you have, the right information what you have, that is very, very important, or the right type of data available, the context of the anomaly, whether the labels are provided or not. Those are very, very important factors when you're going to choose any kind of machine learning model. So that's the important factor to kind of understand where it could possibly fit in. And essentially, it also highlights the depth of the machine learning tools for solving real-world anomaly detection. So these are the main techniques, and as I have said, it's very, very important to kind of at least understand some of these if you are interested about understanding the supervised or unsupervised learning. Semi-supervised is somewhere in middle, but it's very, very important to kind of identify where you lie in those particular extreme cases. So I will highly kind of suggest all of you to have a go and look into that. How does it work, or what exactly clustering means, what regression means, and how classification is being different than clustering, right? What parameters I do not have when I say, okay, fine, cannot go to classification. I am coming into the clustering, right? So that's something I would say is a very great way of understanding how machine learning works. And then from there to we kind of go a little bit into the the future trends of AI and the machine learning of the SHM, and we will see a lot of IoT devices, how they are kind of going to be used. And here you can see that we are talking about the future trends. As I said, we are highlighting, so here we are going to talk about 8 emerging trends here. And the first one is definitely when we talk about machine learning, IoT, we cannot ignore that. That's one of the very useful one, most used one, is that IoT and IoT enabled sensors, right? And this one is, as I said, the most significant advances currently on the horizon. So IoT refers to the network of interconnected devices that communicates and exchange data. And when we are saying about communications, we are talking about exchange of data. So it's all happening in real time, right? So that's the thing we are talking about. So by combining AI with the IoT enabled sensors, structural health point system can automatically collect data. They can analyze data. They can act on vast amounts of data without human intelligence, right? Without human intervention. So that's where the IoT sensors are very, very important, because everything is happening on the real time, right? So embedding IoT enabled sensors across the infrastructure, they help us to gather the real-time measurements of stress. They also help you to get some strain, vibration, sometimes the temperature changes, humidity, and a lot of other kind of the environmental factors. This data then feeds into AI-based analysis system, enabling a very fast damage detection, enabling a very predictive maintenance, and absolutely smarter decision making, right? So that's where this actually always lies. And then this is a very, I think, generalized diagram on the, here you can see that the sensor is collecting the, so this is a nice flowchart where you can see the sensor is collecting the data. Then they are kind of transmitting the data acquisition here, which is this one, right? And then the whole analysis system happens, right? So once this is being happened, then it makes accessible to the online system. That means, and which alerts sent directly to the smart devices, demonstrating that there is some real-time connected nature of the future SDGs. That's a very generic, it can be complicated, definitely. There can be a lot of other add-ons can happen. It's a very simplest way of how this IoT device generally works. When we talk about the SHM cases, when we talk about the infrastructure, this is a very generalized way of we can do that. But now let's try to focus on how it works in practice, right? So these sensors can be deployed in remote, or as I said, that's where we are always interested about, that whether it can be remote or hard to reach areas, whether we can use it. Definitely we can use it. Continuously we can transmit data, create a AI system, right? And this overcomes the limitation of manual inspection. This also kind of makes the infrastructure monitoring more comprehensive. And then AI then processes the real-time data, right? And which allows more near instant decision making. So you can actually understand with the real-time data, the instant decision making can actually happen. You can also detect the anomalies as they occur, or they send the immediate alerts and support the predictive maintenance. So preventing the failure before they happen. So that's how it works. And the combination of AI and IoT, they actually is quite a great combination. They enables the creation of fully autonomous SHM system. So this system can actually operate with little, sometimes definitely you need some human intervention, but most of the cases, maybe 99% cases, you may not need some human intervention unless something goes wrong, right? And then definitely greatly enhancing both the scope and the reliability of the infrastructure monitoring. So the diagram, as I said, this is a generalized way that how integration system works. The sensor gathers data, it transmits the data, and then the internet device or the computers, they kind of sends the alert. And then another one that's also nowadays quite being used a lot, which is the drones and autonomous inspection technology. So currently drones are widely used for visual inspection, right, for bridges, buildings, and other infrastructure, especially, as I said, that hard to reach area, hazardous area, or looking ahead, those drones, that will be integrated with AI powered system, and they advance the imaging technologies like LDRs or thermal sensors. So they are being fitted with some kind of thermal sensors to understand the temperature and the high resolution cameras. So as I was saying, whether there is some kind of cracks being initiated, whether there is some corrosion, so those kind of things can actually be taken care of. And this will allow them to autonomously conduct the detailed structural assessment rather than going there, or measuring the manually. This will actually kind of help to do that without, as I said, without much human control. We cannot say that we are definitely out of human control. We definitely do need human control, but not constant human control or less human control. Somewhere we are saving that, right? So the AI algorithm built into this system will analyze data as again in real time. They will automatically identify the defects such as I said, cracks, fatigue, or the corrosion. So those are the immediately they can identify that the location, the intensity, those can be identified very easily, right? So this capability not only reduces the need of the manual inspection, but also helps environments, as I said, the bridges, skyscrapers, offshore platforms, tunnels, where as a human it's difficult for us to reach. So they can actually kind of take care of those. So as I said, that this is a very nice pictures of, you can see that example of how drones can actually hover around the infrastructure and collect the high quality data to support the predictive maintenance and early damage detection. This is a very nice way of doing it. So currently most drone systems, they rely on the cloud-based process, right, and analyze the collected data. So while effective, this also approach requires a constant connectivity and can create delays, right? That's something is another thing. So in the future, what people are trying to right now do is that they expect that drones to be equipped with more advanced AI techniques or or onboard data analysis, where maybe you do not need a constant connectivity. So that means the drones will be able to process the information locally, right, and operate fully autonomously without needing any server connection. That's how now researchers are working on that, how they can possibly make it, but it could possibly totally work remotely or locally, I would say, without much server connection. So then there will be no connection failure, then things will work out better. So that's the current research is happening on this area. And then the self-contained drones. Self-contained drones are also one of the the very famous research area among UAV researchers, and they will be actually ideal for inspecting the remote or isolated infrastructure, as we said. So they will reduce the manual labor, they will increase the frequency of the inspection, and they will improve the safety in the hazardous environment, right? So essentially this shift actually moves drones from being just the simple data collection methods to the very intelligent agents capable of the real-time analysis and immediate decision making. So still we are kind of doing a lot of research with drones because of the connectivity, and it's not still the fully autonomous system. But I think now the drones are being kind of, or people are trying to use it more as an intelligent agents rather than just collecting the data. So that's where the kind of research is kind of moving around into that. And then among the 8 ones of the future trends, you can see that, so here you will see that we are going to talk about a little bit about what is being done, what is currently happening, and what we are going ahead from the current trend, right? And that's why we are talking about the future trends where we are lying around. And there are currently eight of those, right? So the third one is advanced sensor technology and fiber optics in the structural health monitoring, right? So when we talk about the cutting edge sensor technology, when we talk about the more advanced technology, as I said, that the fiber optic sensors are very important one, because it can actually, at a time, they can actually take up multiple sensors or multiple data. So we are transforming the SHM by providing continuous real-time data on parameters, as I said, that strength, temperature, or any kind of other structural factors with exceptional sensitivity. So fiber optic sensors, they are particularly useful, as I said, for the large-scale infrastructures, definitely bridge, dams, tunnels, because of their durability, precision, their long-distance coverage. They're quite being used a lot. So now if you're trying to look ahead, you can see that this AI system will process data from this system in real life or the real time, and they will actually help us or enable us the early detection of the anomalies and giving the engineer the valuable insights into the long-term structural behavior. So as these technologies will mature with time, AI-powered SHM system will achieve greater accuracy and provide more nuisance or more actionable insight into the health of the infrastructure as well. So that will again reduce the risk, that will improve the maintenance, extend the lifespan, help the economy. So those things will automatically add on, right, when this is gonna happen. And then again, the fourth future trend, which is happening quite a lot when we talk about the machine learning algorithm in the structural health monitoring system, is the real-time monitoring and early warning system in SHM, right? So when we talk about the future SHM system, that will go beyond just continuous monitoring. That means that they will integrate the real-time early warning system. So what does possibly it mean? That means that the system won't just observe it, but also predict and alert immediately. So you can imagine that you are measuring the cracks with the drone, and it is giving you the data, and it is actually telling you, okay, fine, there can be some different issues, or there are some differences in vibration, stiffness, frequency. So, but now what is happening is that they are trying to AI and predictive analytics together, so that this will not only observe the data, they will analyze it immediately, and immediately they will kind of alert it that there is some issue, right? So basically what we are trying to do is that we are trying to match AI and predictive analytics that will process in real-time data from sensors to the forecast potential failures with a much higher accuracy, right? For example, if you think about the seismic prone areas, so AI models could actually estimate the impact of the earthquake on those buildings immediately and bridges, and then immediately trigger the. I think that happens quite a lot now. You can see on the mobiles and all, we can immediately get some evacuation responses, emergency responses if some other issues happen. This kind of capabilities are being still people are working quite a lot in this, and this actually enables the dynamic risk mitigation strategies as well that will help to prevent infrastructure disaster before they can occur, and they will also reduce the damage, they will reduce they will save the cost, they will save the human life, improve the public safety as well. So essentially this represents the shift from reactive to predictive infrastructure management. You can see that how this is processing by using a AI as a real-time decision support. So basically now we are not only interested about the understanding the damage, but how proactive infrastructure management can be done using a AI as a real-time decision tool is something people are working on. And then I think the role of digital twin, as I was saying, definitely we are not going to cover digital twin in this course here, but that's very, very important for you to understand how digital twin works and what exactly we mean by DTs, right? DTs are basically the virtual replicas of the physical assets such as beach, tunnels or models. So in the future of the SHM, so DTs will be continuously updated with the real-time data from the sensor, which is being embedded in the physical sensor. And this will allow the AI to simulate the different scenarios, analyze the structure's response to the stress, and then also they kind of predict the future performance, right? So by integrating the AI and DTs, the structural health monitoring system, they will be able to simulate the long-term effects of environmental factors, loading condition, maintenance. So basically you are making a DTs or digital twin of a real-life structure, but those real-life structure with the sensor are feeding the data continuously to the DTs to make the DTs updated or real-time, right? And this actually provides a very highly accurate prediction of when and where the damage is likely to happen. So that's where the DTs are quite being used. So this approach will revolutionize the infrastructure maintenance, moving from reactive to proactive strategies. And instead of waiting for something to break, something to happen, as an engineer, we can plan the inventions in advance, reduce the risks, costs and downtime while improving the safety and reliability, right? So, do you want me to give like 5 minutes break and start, or you want like a continuous one? You can take just a 5 minutes break and we can start at 4-5. one, we have now talked about the role of digital twin, that how it approaches revolutionizes the infrastructure maintenance and how it is kind of moving towards the proactive from reactive to proactive strategies, right? Instead of waiting something to happen, we can actually plan the inventions in evidence, right? So the next one is among those 8 is that advanced data analytics or the blockchain of the data integrity, right? Here you can see that that's the so when we talk about this advanced data analytics or when we talk about this blockchain for data integrity, structural hegemony system, they actually generate a massive amount of data when we kind of think about this IoT sensors or IoT enabled sensors. So advanced analytics including deep learning and artificial neural network as well as ANNs, they are very crucial to uncover the hidden patterns or correlations are the early indicators of structural risks or failure. And so the managing and storing the terabytes of data produce this daily presence is challenging for the scalability. They cost also retrieve speed and traditional storage systems sometimes offer struggle to keep it up. And then another one is the blockchain technology that is also emerging as a potential solution. It can secure the data integrity. It can also ensure the authenticity and provide the tamper-proof records and sensor data. So when combined with distributed cloud storage and advanced compression methods, the blockchain can actually help to address the issues of accessibility, data accessibility, or security of the data, which we are quietly worried about, especially when we talk about some kind of certain cases, right? So this combination of AI-powered analytics with blockchain data integrity, they will always or they will help us to represent a major shift in structural health monitoring. It will enable the highly reliable insights. It will also secure the data exchange. When we talk about the large data, how to store this data between the stakeholders, right? And better decision making for infrastructure maintenance and risk mitigation. So that's the way that this advanced data analytics or the AI data analytics are kind of combined with the blockchain for the integrity. But why we need that? So when you think about the structural health monitoring applications, how they are kind of growing from the past few years, we definitely does the volume of data being generated, as I said, for the IoT or drones, and that's the reason we are kind of using the blockchain. So how blockchain is helping? Blockchain actually offers a immutable tamper-proof ledger of the sensor data that will help to maintain the logs and system activity. And this will enhance the transparency, this will safeguard the data from manipulation or the loss of the data, right? Which is actually crucial for the large-scale projects. And how it is being integrated with the AI? So when we combine AI with the blockchain, that can actually validate the data integrity in real time during the processing of these data, right? And that is going to help you, or that is actually ensure you the data accuracy while enabling the instant anomaly detection. You are basically detecting the anomaly, but you are also kind of accurately doing that and securing or sharing the information between the people, right? Between the engineer who are analyzing the data or from the drone to analyze and to predict and further to get back to the another engineer who may kind of take action on that. So that's going to be safe when we integrate the AI with the blockchain in a real time, right? So this synergy between the AI and the blockchain, they actually strengthens the SHM system a lot, making them more reliable, making them more resilient, making them more transparent, even as they scale to handle growing data volumes from multiple resources. So in short, what we can say is that the blockchain technology can become a cornerstone for secure, trustworthy and future-proof SHM system. So now another important one among those 8 is the 7th one, which is the 5th generation cellular network technology, which is enhanced for connectivity for SHM. So the rollout of the 5G network, that is dramatically going to be improved the capabilities of the AI powered systems. So 5G mainly provides the the ultra low latency and the high speed connectivity, where we are talking about the drone, where we have an issue with the connectivity. So that's where this actually helps a lot. That help you to enable the real-time data transmission from IoT-enabled sensor, drones, as I said, and other devices, even from the remote areas also. So how this is being enhanced? This actually enhances the connectivity quite a lot. That allows a very seamless integration. When we are discussing the drone, we were thinking that, or we are discussing, that's one of the connecting issues when we discuss with that, especially when you have a vast number of sensor networks, right, for the IoT cases or those kind of cases. So AI system can actually process those data instantly and improve the speed and responsiveness of the monitoring. So that's where how it actually works out. Impact, as I said, that when we talk about this 5G, the structural health monitoring system will enable to monitor the large scale infrastructure more efficiently. They can also provide instant feedback on the structural health and trigger the immediate interventions if anomalies or potential failures can be detected throughout that period. So in summary, what you can see using this fifth generation or the 5G, they kind of act as a very strong backbone for the next generation structural health monitoring system. They also enable us to continuously real-time insights and faster decision making. And the large one is that the large-scale SHM or the AI-driven maintenance system, right? So when we talk about the large-scale SHM, what do we mean by large-scale SHM? Are we talking about as a sensor system, or we are talking about IoT? What do we mean when we talk about large-scale SHM? Yes, yes, right, right. So when we talk about the expansion of the SHM scope, right, as AI and the related technologies, they advance, the structural health system no longer be limited to the individual assets, right? They will expand to cover the entire cities sometimes, right, or entire regions throughout. So we give a company that okay, you need to monitor the entire region, right? It's not only about we are talking about one building. It's not only about we are talking about maybe one small village. So that's where we are kind of expanding the SHM in a larger scale through the centralized AI platform. So now you will see that when you kind of see these traffic systems, mostly you will see in US it's quite common that you will see always the cameras are being hanging around on the roads because they are kind of always not only seeing who is breaking the rules, they are monitoring the traffic, they are monitoring several other perspectives and they are detecting that. But you will see that that's always been connected not only for the one road but for the two cities. And there will be one company who is actually responsible to take care of that. And that's where the whole large scale structure or the large scale SHM systems comes on. And when we talk about those, you can understand we definitely cannot go without the IoTs, or we definitely cannot go without getting into the data, big data, right? And that's the reason we need to do that with the centralized AI platform. They always kind of try to develop a centralized AI platform which will generate the data. That means that can be supervised, that can be unsupervised, that can possibly happen that okay fine, at this period, this much traffic is quite expected, right? So they do have that division, right? Or maybe it could possibly happen that they know that okay fine, there could be an accident, but there may not be that situation could possibly happen. So why that happened, right? So that could be an unsupervised case because they don't have the data, they don't know what happened. So there can be variations of that, but they do actually develop an AI platform to take care of that big scale rather than just individually tracking down news, right? Similarly, we are talking about the roads here, but if you will see most of these UK cities, they do have a very similar pattern. I don't know how many of you have visited UK. Similar pattern of houses in the same cities, it's always like that. So that's also some way they kind of monitor the temperature of the particular place. They kind of monitor the all other aspects of this. So that's also some way they kind of taking care of those, and that's being always done in some kind of platforms. Now it's moving into the AI platform. And the real-time multi-asset monitoring is very, very important in those cases because we are talking about the large-scale SHM that will simultaneously monitor multiple infrastructure assets. That means breach, and sometimes it could possibly happen that we are talking about the whole city. So in that case, we are not only kind of talking about the breach, we are not only talking about the roads, we are talking about the whole city perspective. That means we are talking about bridges, we are talking about roads, tunnels, buildings in the whole city region, right? So you can understand how big the whole monitoring system would be and how complex the monitoring system depending on their interest. So by integrating this AI-driven decision at a scale, cities will become more smarter, they become more safer and more resilient, transforming more urban planning. Now there's a lot of this kind of urban plannings are happening in many of the cities in India and infrastructure management. You can actually monitor the infrastructure, you can manage the infrastructure through this. So in essence, actually, the train moves SHM from isolated system to network one. It can also move to the intelligent unified resolution. It's paving the way of smart cities as well. So that's the one of the very famous one is currently being happening. So now we have talked about all eight future trends which will possibly happening or gonna happen throughout this. So among the eight trends, which one do you think is going to be the most emerging one, or do you think which one could be the most interesting one? Do you remember all eight of those? So we have started with integration of IoT, and you can see somewhere it's all are connected. It's not like we are talking about individual of those. These all are connected, but it's actually being developed in one of the area quite a lot compared to the other, right? So we have talked about integration with IoT-enabled sensors, right? We have then talked about drones, quite being using a lot, but still we are struggling with the connection process and those things. Then definitely the advanced sensor technology, where fiber optics is a very, very important part, but there can be other type of sensors as well. Then the real-time monitoring. So when we are talking about real-time monitoring, not only the monitoring, but we also want the early warning. We do not want to only be monitored. We also want to get the early warning that okay, fine, this is not working. So we need immediately kind of take some action. And then the digital twin, as we say, that we kind of develop the exactly the real life structure through the sensor. We are sending the data. We are actually making a real life structure through this DB and try to understand how it could possibly behave, right? And then the data analysis blockchain, as I said. And then the fifth generation of 5G, where the technology or the connections can be more advanced, so you can actually get real-time data more faster, more better. And then definitely the large-scale SHM and AI-driven maintenance system, right? So which of those among eight you think that is having more better future compared to the other? Yes. Sorry. Digital twin, why do you think that?
Because it's practically more possible to apply this technology in the current scenario.
But do you not think that when we try to actually build something which is in the real life and build something on digitally, there will be so many uncertainties that we cannot take care of in the real life. Like in the real life, there are so many uncertainties, right? But we cannot put all those uncertainties in that digital system. So don't you think that that's some way kind of pushing us to understand how the real life things would work out?
But compared to other options we have, real twins offers better possibility for the monitoring purpose. So I thought this
Yeah,
would be
yeah. Yeah, definitely, absolutely. I think that's something we are kind of working quite a lot. And the main challenge is, as I said, that to kind of build something or take care of the uncertainties in the real life system, right? And anybody else? This one. And why do you think like that?
Information about the system. AI can itself, using neural networks, or if we have some data, even if the data is scarce, if we have the differential equation, we can use it in a physics informed method. So
Yes.
that's why in AI driven system, even we have very limited access about the physical understanding of the
Yeah.
system, still it can
Absolutely.
predict anomalies and give some kind of warning.
Yeah.
That is not in literature. What is maybe the mathematical model has not been framed, but still AI can detect.
Yes, absolutely. Especially when we try to do this experiments, right? It's always not possible. Not everybody may have the accelerometer, oscilloscope, or maybe not able to kind of manufacture the structure. So that's the way that we do not know how the data could look like. We do not know how the distribution could look like. So we actually generate the physics informed one, and definitely that always is an important one. But again, the challenge is that we may not be perfect. We may not be able to kind of take care of a lot of uncertainties which could possibly there. Maybe it could possibly happen the whole distribution we are imagining. that can be wrong. And that's the reason I know we kind of think, okay, fine, it would behave like a normal distribution. We take it like a triangular and we try to make it like little perfect. Absolutely, that's another important thing as well. Anyone else do you think that? Yes.
Why cannot we just mix two trends like
Sorry, I cannot hear you.
that we can mix two trends also like
Yes, absolutely, you can do that. And you can see that all of these are so much interconnected. If you see that none of these are like very, very individual.
like if we take digital twins and AI driven then we can all solve like most of the uncertainties.
Yeah, yeah.
While taking the real life replicas and by monitoring them with AI, we will like solving many problems that we cannot do from a single trend.
Yeah, yeah. So when you use this AI driven, why do you need to actually make the digital twin? Because some way it's kind of coming under the same umbrella, right? Then you don't need to kind of invest on the digital twin. You can immediately use your AI driven techniques and do that. You don't need to kind of make the digital twin, right? And even if you take the digital twin, then how you are actually implementing the uncertainty, which is not, you cannot take care like the real life one.
AI driven is continuously monitoring all the uncertainties. So I thought like if we have a digital replica of the digital twin,
Yeah, yeah.
then we are monitoring them with AI with the help of AI. It will be better helpful.
So when we talk about AI-driven monitoring, it's actually not giving you the real-life thing which is happening on the experimental or happening the practical perspective. So AI-driven monitoring means what sometimes you do not know how your distribution looks like, you do not know what your data look like. You may not have data also. Sometimes create the data, right? Or sometimes you have some missing data. Sometimes you have some misinformation. So those are the things you kind of definitely work along. But how can you actually kind of make a real life scenario with the AI driven? Can you do that? Especially when we talk about digital twin. Do you think that it someday comes under the same umbrella?
AI can predict the data with the help of like with the third method, advanced meta analytics, with the help of CNN.
Okay. Now I'm saying you one of the very simplest one, right? So if you think about we are we are manufacturing something, right? During manufacturing, there is some manufacturing effects, right? So how will you take care of that using the AI when you talk about real life digital twin? Can you actually take care of the manufacturing defects which happens in the real life in the structure when you are designing computational data? You can do that. Absolutely, you can do that.
While modeling, we can predict the defects. We can see what is maybe the load carrying capacity
Yeah.
in the FEM model.
Yeah.
And so that we don't have to do actually there's some parameters we can relate.
Yeah.
Which had to be present in FEM model, but which is not
Yeah.
present, that we can.
Yeah, you can model it, but definitely not the ideal scenario. That's the still now digital twin is some way struggling compared to if you see the other ones. How about the others? What do you think about the 8 cells? Which one do you think is like having more capacity compared to the others? Just a discussion. You may be wrong, I may be wrong. That's fine. What do you think about it? Yeah. Anyone else? I want to hear who didn't answer.
think man, AI and blockchain integration is also
Sorry, AI and?
blockchain integration.
Yeah, why do you think like that?
Because like nowadays hacking a system, putting something in the actual data, right? That is possible. So we need to make sure everything is secure. Actually,
Yes,
integration of blockchain is very important.
Definitely. That's one of the very, very important factors, that the security of the data, and how you are kind of taking care of those so many large sensors. That's very, very important as well. And I think, especially if you are in computer science, if you are into a lot of data, that's one of the biggest worry as well. Any other options do you think that will be useful in the future trends? Nobody thinks that the early warning is very, very important.
Yeah, good thing.
Anyone? Which one do you think has a more future aspect among these 8?
The eighth one only, the large scale SHM application. Because right now we do not have a lot of SHM capability.
Especially when we talk about the large scale one, right?
Large scale one, so we need to have even the sensors, they are very costly.
Yeah.
So a lot of people don't know about sensors. So once we have enabled one infrastructure where sensors and use of sensors is as common as other methods of structural testing, like ability testing, then we can think about more things like more.
They have so many. They have kind of so many sensors. It's all about that. Definitely the sensors which are cheap or easy to install. They are brittle, like PCT ones and all.
That also costs 1,000, like one sensor because.
Yeah, and then that does not run for a long period of time, right?
Yeah,
That's
that
another
will not
thing.
run. So I feel like if we can have large scale SHM infrastructure first of all, then we can have more human resource working on it, and then we can think about other things. Like all other factors can depend on it. When we are
Absolutely,
building
absolutely.
the
Yeah,
capacity.
that definitely is one of the important factors as well. But yeah, I think I will let you guys kind of have a thought about that which one could possibly be more advancing. But if you will look into that in other perspective, you will see that all of this has some future. And that's also the reason that I have selected those 8 important ones, rather than there are many others one also. But those are the main important 8 methods or techniques that currently being doing research a lot. And then there are a lot of advancements they are happening, and they are not like individual, they are always interconnected. If you look into all of this, they are always interconnected. They still do have a lot of disadvantages, and how you can actually take care of that. That's the currently research and advantages are they're trying to find it out. So now let's try to see one or two quizzes into that. So when we talk about which one of this is not feature of digital twin, when we talk about when it's a real-time data, C, right, because it does not repair the structure, right? Yes, you want to say A?
Relates to the eight thing, which have something to ask.
Yes.
So recently there have been some studies on multiple drones converting themselves into sensors and bringing lands to the bridges, and then they have both visual and data.
Yeah.
So it's a fusion of both visual based visual inspection and data collection.
Yes.
Which is one thing, and I think that is missing, where you have a fusion of first and second point.
Yeah,
And there is
yeah,
also
yeah.
a crowdsourcing of data where you have weighting bridge interaction studies.
Yeah.
Where you get the data from the weighting, but still you understand about structures. Isn't it also not part of the future consensus?
Yeah. So if you look into this one, so that's the one where we kind of mainly talking about all the perspectives of the drones. It can be actually kind of taking the images and analyzing it. But the main challenge is right now, if you will look into this UAVs or the drones, is that the connectivity. And that's where definitely 5G is doing really, really good. But I think still the problem with the drones is that when we talk about the real-time one, sometimes if the connection goes or then you lost, then you will not be able to do that. That's the current, I think, only the disadvantages more into this drones, because drones are very lightweight, and there are a lot of research is being done that how to make that particular airfoil or the small ones, how make it more user friendly, so that you can attach more kind of laser points, or you can attach more the ways of to kind of take this thing, and some way that there will be very small place that the drone, that place can, the airfoil can go inside and take the photos. So there are a lot of researches are happening to make the drones very user friendly, and we are kind of working it, going to make it more lightweight, like using some kind of composites. We are designing a lot of those into that as well. But the challenge is still now for the drones is that the connectivity. So that's some way we are still kind of, I think we all are working on, and then that is, I think, one of the challenge. But what you are saying, it's all coming under the drone that.
I was talking in terms of the fusion of the
Yes.
and also the data from which we are trying to get from the sensors.
Yeah, that I think that some way is still happening, right? There are a lot of this, even in India also there are like CSRI projects are happening where they are kind of, I don't have the pictures with me, but I have few colleagues who are kind of working on those, where they are detecting the damage of the bridge by using that.
They are detecting, but that's never actually implemented in the numerical models.
Yeah.
Visual damages.
Yeah, absolutely.
As you
Yeah.
said,
Yes,
uncertainty
absolutely.
is-
Yes,
that's one
yes.
part of the uncertainty.
Yes, absolutely. Yeah, that's definitely one of the very interesting ones. Because I think still that drone part is still in between. It's not quite advanced some way. If you will talk about UK, especially this does not kind of quite. People are quite interested to make the drone lightweight, make it very fancy, and make it reach to a place where it cannot. But not much interested into using that to monitor the infrastructure. But it's being used quite a lot in US, even in India as well. And I know that there are still so many fundings are there from the I think MHRD and all where people are trying to do that. But yeah, absolutely. Uh, Predicting that and then coming back into that's still some way not much has been done, and that's a very good way of combining two and making a very good future trend. But I think I would really like to kind of see to take care of the connectivity because that's I think always a challenge from the last so many years. Because I think now they have quite able to make it lightweight. So we will be literally finding small around 40-50 pounds in UK. We get these small drones which are very user friendly. But yeah, again, if the connection goes somewhere, you can't go very far. So if you think about a very large structure, you want to kind of monitor it from a very far distance. That's little tricky. That is cannot be done using drones. So that's something I think people are trying because we are always interested about the large structures. We are always interested about the real-time monitoring, understanding the damage quite early. So that's the I think the gap this drone currently facing in that. I mean, it's okay with the small structures or the range is very small. But when the range starts becoming more, when you are far from the connection, that's the main issue actually kind of happens a lot.
Adding to this, actually, you have did some research on digital twin in mechanical, generally, or in spatial aeronautics. The digital twin is almost 99% of 90%. In civil engineering and structures is always, it is, as far as my knowledge is concerned, I think we are still not even reached 80-82% of
Yeah.
actual twin part.
Yeah.
So
Because
any idea what you
yeah.
that part of this?
Yeah, absolutely. I think if you think about digital twin for aerospace or civil structure, it's very challenging. Why it is challenging compared to the mechanical one? Because there are so many factors always affecting in the real life compared to the mechanical cases, right? There are so many corrosion case happen, there are so many fatigue case happen, there are so many environmental factor happens. But if you will not only see the civil one, if you will see the aerospace one, still the same. There are not much achievement or it's not maybe aerospace is very less also compared to civil. Civil is still like around 70 to 80%, but it also depends on the factors which is happening in real life, whether you will be able to kind of taking care of that on the digital twin aspect. So in civil structures, the aspects or the effects are always much more in the real life scenario, and giving that into the the digital twins is really challenging. Because I think in mechanical it's not quite challenging if you compare the environmental factor, the outside environmental factors, or the other like corrosion, those things, the little bit complications. But in aerospace, it's much more complicated because you are talking about the human safety in a large scale. So it's not quite easy to kind of take care of using the DT. So DTs are still, are still I started working on that, but not anymore much because it's still a very kind of challenging some way. It's still kind of, it's more like using the AI that it's kind of giving you something which you are looking for, but you may not know whether you got the correct one. But still you need that. So because you are talking about the large scale complex data, you cannot avoid that, but you have to be really very kind of clear. You have to be very careful about trusting those or using those. You have to be really careful about what data you need or how. So yeah, these are still kind of, I think it's been using, especially for the IoT cases, being used quite a lot from the last 5-6 years. But for the civil aerospace, you forget. I think people have now stopped thinking about it. But civil, I think still getting the performance is not more than 70 also, I think. But still people are kind of working a lot onto that. Yeah.
Can I ask in Hindi?
Sorry?
Can I ask in Hindi? Because I'm not.
You can ask in Hindi, but my first language is not Hindi. But I can try to answer you because I understand and speak a little bit of Hindi.
How can an AI model trained on one bridge adapt to another without new label data?
Can you repeat again? Sorry.
How can an AI model trained on one bridge adapt to another without new label data?
Yeah. So how can AI model can reach to? Can you say the last sentence?
Probably his question is
Yeah.
suppose you have trained AI model based
Okay.
on one bridge data.
Okay.
So how it can be applicable to other bridges?
Are you
or
asking for the other previous one, right?
Yes,
Yeah, absolutely. So if you will look into the anomaly detection, right, what did I say is that you have to understand the contextual one, right? If the bridge is in the same region or in the same city and their temperature or those things are same, it is going to be designed as the same loading condition, right? So that, or in the same city you would say that. Then somewhere it will have some kind of similarity. But still you never know that at what point the traffic will be more, right? Or that the material has been used more. And then the main biggest uncertainty is these contractors, right? What kind of materials they have used. Maybe you have used same design method for same bridge, right? And same contractors have actually done the board. But you will still see the performance variation in both the bridges. So it's very rarely possibly happen that you have trained your data for one bridge or or you can actually that going to be absolutely fit on for one the another one. I mean, it can have some similarity if it's in the same region, if the population is same, if the traffic is same, you have used the same material, the design is same, but it's never gonna be like as ideal for both of them. Not only bridges, for any cases. Is that clear? Is that clear answer?
I think this is why when we are developing some AI technology, what we do, we train the AI based on the history of one particular architecture and the response as well we give it to the AI and the physics as well, and based on the response and the earthquake data, we train that, and that AI is only able to predict the response for that structure and can generate result for that particular structure, because if the structure changes, the mass matrix stiffness and all those things are changing.
Yeah, so we cannot actually kind of define one model for any other structure. It can be in the same region, it can be actually made by same engineer, exactly same way, the design can be same, but it never can be used for the same. There will be some kind of differentiation always. And then there are like those things are always there. But yeah, there can be similarity, like the earthquake region or the traffic, temperature, many things. Not only about bridge, I'm talking about the buildings and other cases also. So that's the reason you will see that even for when we model this AI predictive model for the whole city, all of the buildings they are not being taken care all together. So everything will be modeled separately using the different sensors, and then they will feed into the data. So it's never going to be possible that you train one AI model and that's gonna work out into the other proper like 100%. So once the structure will change, your whole model and everything is gonna change. A lot of uncertainties will come into the picture. Your matrices, those things will also kind of be taken care of. But yeah, similarity will be there if it's in the same. So it's definitely a learning process that if you learn about something, you can use it for the different kind of structures as well. Anybody else have any other question? No? Okay, fine. So let's see the next piece. So which one of the following not a benefit of integrating IoT and AI when we think about infrastructure monitoring? C? Why not A or D? Yeah, right. So C is the correct answer, right? Because self-prepare is definitely not possible. So now let's see the next one, which is the digital twin in SHM. So which one is the correct answer? It provides the real-time updates of the physical assets, or it simulates the different scenarios. Sorry? All of them, right? When we talk about the digital twin. Do you have any further questions what we have seen just now? Do you have any questions of anything that we have discussed now? Yes.
I have a different question. Where can we get the data? Is there any place where we can where repository of a large database is
So data about what data you are talking about?
about the structural health modeling, the signals data only. Is there any repository where all these data?
So that's why we use the sensor to generate those data, right?
Is it present somewhere that?
So no, that's where this comes of blockchain and all, right? The people definitely will not be kind of sharing the data with the outside. Then definitely there are some websites where you can get some rich data. The people have done that. There are papers, recent papers. But in general, basically it's always the real-time process. So there are some websites for some certain. I can send you some for certain kind of structures and all. You can get those data, but they are not definitely real-time. But people have monitored it for like 5 years, something like that. So there are those. You can actually use those and kind of try to understand how it could possibly look like for a certain type of structures.
I mean, California pure strong instance database and CSNP database are available online.
No, for even for the Indian bridges also there are some websites where have so where people have actually kind of did that. So if you're interested, I can send you some. But there are kind of definitely lot of limitations, and for the earthquake data, so you will be finding a lot of those earthquakes because I think that's quite online available compared to the others. So definitely there are some, but I mean when you kind of use those, then you have to kind of little bit careful about what structures you are using, and whoever monitors the data. I think it's always like understanding those data and relying on the data. I think it's always a little bit tricky. But there are websites, and especially in India also, I think there are a lot of websites people do use it. Even for there are a lot of actually articles where people do share the data on the earthquake engineering. So if you're interested, I can send you those details as well. So anyone has any other further doubts? If not, then I think let's quickly look into the summary, and then I will also tell you some of the future things. Maybe you can look into that not before coming to the next lecture, but it's very important to kind of understand that. But I think today what we have seen, if you can look into this, we have understand the key takeaways of all the 8 trends. And so we have started with IoT, we have started with IoT enabled sensors, and from that we can bend to the drone, understand how the autonomous system works out. Then the advanced sensor technology that comes with the fiber optics, right? We talk about high sensitivity, we talk about real-time monitoring of the large-scale structures, and then comes the real-time monitoring and the early warning, right? Where we talk about proactive risk mitigation, we talk about disaster prevention, and then comes the digital twin in SHM, so where we kind of trying to include a virtual replica of the physical assets we are interested to monitor, and then update the real-time sensor data to that scenario simulation to have a predictive analysis, right, or to have a predictive maintenance. And then comes the, as I said, the advanced data analytics or blockchain. So we are talking about the security here. We are trying to ensure that the secure tamper-proof data has to be there so that we can manage the data at a larger scale, right? And then comes, as I said, that the 5th generation cellular network, which is the 5G network. So that actually help us to understand the ultra low latency that will give us very high speed connectivity, enabling a very seamless real-time data transition from sensor to the drones, right? And then the last one is the large-scale SHM or the AI-driven maintenance system. So that's basically helping you to understand the centralized AI platform and helping you to manage the city-wide infrastructure, or some way I would say country-wide infrastructure, health or smarter, safer and more resilient system. So you can see from all of these particular key takeaways that artificial intelligence or some way machine learning, they are transforming the structural health monitoring from isolated reactive systems to a more integrated one, right, more predictive one, and more city-wide resolutions. So that is actually paving the way of smart infrastructure, that is paving the way of sustainable urban environment.
I think there is one more participant who wants to ask something.
Okay, we can take the question, I think.
Yeah.
Can you see the? I cannot see the screen.
Oh, okay.
Yeah.
I can see.
So maybe we can take the questions after this has been done, right? Yeah. So so that's the kind of summary we kind of see from this particular trend, that how the isolated or reactive systems to the integrated predictive systems, the SHM is happening from the smart. It's happening as a smart infrastructure. It's happening as a sustainable environmental trends. So I would kind of highly suggest you to think about it, that if you think about one particular real life infrastructure project, you can think about bridge, you can think about tunnel, you can think about any offshore structure. So what type of monitoring are used? Whether it's a structural monitoring we need, whether we think about the environmental one, or we are thinking about the functional one. So think about one of those particular type. and then think about, are the systems proactive or they are reactive, right? And think about why they are proactive, whether we are interested about SHM or we are about environmental ones. So if you are interested about environment, whether the damage has actually been introduced or we are kind of thinking about before it has been introduced, right? And then once you think about that, then you come into the second part of the lecture. In the second part of the lecture, what we have understood that how this AI, IoT or the digital twin can monitor the strategy. So now first you think about what kind of monitoring you are interested about, right? Take any kind of structure, think about what monitoring you are interested about. Once you want monitoring, you select, then you select whether you want to monitor it before the crack has happened or you want to monitor after the crack has happened. So once you select that, then you use one of this AI or the future trends and try to relate with that and understand how you can improve the strategy. So you have the SHM monitoring, you use it for the proactive by using the digital twin or by using the blockchain. Can you actually make it improve? And if you can, then why not the other one among the 8, right? So I think this is a very good task, I will say, to kind of go through and understand the whole process of whole lecture 1 which happened, so that you can have a better idea of what we have learned throughout today, right? You can take a photo of this if you want to. This is basically the whole day task what we have done, okay? And again, as I said that, I will always kind of give the references from everything, whatever we have discussed today, as well as everything you should actually go through if you want to kind of learn more things, relevant to that. And so these are the references for the lecture 2 part today. So you can, if you are interested, there are some papers, there are some books, some encyclopedia. So if you are interested, please go through that. So most of the things, all of this, whatever we are going to cover, will always going to be added as a reference. So once you go back, you can have a look into that, right? If not, then I think thank you everybody for coming today. And this is actually my website where you can see we do a lot of machine learning, digital twin, more into the structures and mechanics. So if you're interested, you can always look into what we do. We do a lot of interesting things, and you can always email me too if you have any doubts. So we will end the lecture today, and I think I will see you all tomorrow, right? Thank you very much.
One question from all.
Yeah, I'm just trying to see that. Yeah, so can you see the screen? Sorry, I'm not able to. What's the problem? Can you see the question, Shamim, and let me know what
Yes,
is?
yes. The question is,
Yeah.
this one, can we infuse quantum ML in SSM?
Yeah, so there are, okay, so can you tell me the name who is asking?
K. Anand Babu.
Oh, I think also, can he help me? Because I think I'm.
Yes, I think he
Okay,
can.
okay, I think he can hear me. Okay, perfect, yeah. So yeah, quantum ML is actually been another research area. So it's been actually, we also call it as a QML. So it's been used a lot, little bit on the SHM because it's a promising area, but less work has been done. It actually anomaly detection or the future extraction from the sensor data. Also, it's a very early age. There are not many research has been done, but definitely it has the potential like faster taking the data more faster, or ability to have the process the less data if you have less data, which are particularly benefited when you have data limitations in SHM. So, but it's still kind of new research area, but definitely we can use KML in the SHM. Any other questions of you? If not, then thank you everybody for coming today, and I think I will see you all next tomorrow. Right? Thank you.